Hello, this is Professor Kuehn. We've been talking about Chapter 8 in a student's guide through the great physics texts. This chapter deals with the work of André-Marie Ampere, specifically his work on the relationship between electrical currents and magnetism. We haven't yet got to his description of magnetism, but we have been focusing on his detailed description of how an electric current arises. You might remember we mentioned that if we have a voltaic pile, a battery, the chemical reactions within the battery produce an electromotive force. That is a force which tends to try to move electricity. That electric force, that electromotive force, if the battery is connected to objects, can create objects that are in a state of electric tension. So, for example, if we took two metal spheres and hooked them up to the opposite terminals of a battery, the electromotive force arising from chemical reactions would move positive electricity into one of the spheres and negative electricity into the other sphere. These two spheres would then be in a state of electric tension. Today we would probably say there's an electric potential difference between the two spheres. An electric potential difference is measured in volts. If then, as he mentions, an electrically conducting body, such as a wire, is connected between those two spheres, the electric tension gives rise to an electric current. And that electric current can be measured using a galvanometer. Recall, a galvanometer is basically a compass needle that, when placed near an electric current, is deflected, as Ørsted has shown us. If we look at page 87 in the text, he talks about the direction that a compass needle is thrown, as he says, when it is placed near an electric current. And he uses this example. He says that let me see if I can find it, if one places oneself in thought in the direction of the current in such a way that it is directed from the feet to the head of the observer, and that he has his face turned toward the needle, the action of the current will always throw toward the left that one of the ends of the needle which points toward the north, and which I shall always call the austral pole of the magnetic needle. So the picture he has in mind is, imagine that you are lying down, so here are the bottoms of your feet. You place yourself like this, so here is you laying down. Okay, that's you lying down. And you are lying down in the direction of the electric current. So you're imagining the current passing through you in this direction. And he says if you're lying down and you're facing a compass needle, like this, and that compass needle is pointing toward the north, that compass needle, once the current is turned on, the part near your head that you're facing will be thrown in that direction, that is toward the west. This is the way of remembering the way that the compass needle will be thrown. Of course, we could use a right-hand rule, which gives us exactly the same picture, that if we take a wire and we have a current going through it in this direction, and then we wrap our right hand around this wire so that our thumb points in the direction of the current, we'll arrive at a magnetic field that is going around in this direction, which is the direction that the compass needle will point. Okay, so this is what he talks about on page 87. He also mentions around this page, and perhaps it was the previous page, that the galvanometer can be used to detect the direction of the electrical current both in a voltaic pile and in the vicinity of the wire connecting the terminals of the voltaic pile. So let me show you what he's talking about here. If you imagine the voltaic pile having a copper and a zinc plate, I'm showing kind of the internal parts of the voltaic pile. So this is the positive terminal, the copper terminal over here. Here's the zinc terminal, the negative terminal. And then if you connect a wire between these, well, which way is the current flowing in the wire? Well, from positive to negative, that's the sense of the electric current, and you can figure that out by holding a compass needle near it and determining which way the compass needle deflects and find the current goes in this direction. What about inside of the battery? Well, inside of the battery, if you hold this galvanometer right next to the battery, you can find that the current is flowing likewise in this direction. So it's the whole thing here is flowing in a clockwise direction around the circuit. Don't be confused that the current is flowing from the negative to the positive terminal inside of the battery. Why is it doing that? Well, it's because there are actual chemical reactions going on that are driving current in this way so as to create positive charge on the copper terminal and negative charge on the zinc terminal. Okay, now what we'd like to do is move on. This is all kind of preparatory work in order to understand the experiment that Ampere carries out. And this is described on page 88 and 89. So let me just show you briefly the apparatus that he's going to be using. This is shown in figure 8.1 on page 89. And in this diagram, we have a wire that is suspended, and that wire is labeled XCDY. That is a metal wire, and through that metal wire, one passes an electric current. That wire is hanging above another metal wire, that is wire AB. And if a current is passed through wire AB and through wire CD, we can talk about how he gets the currents there in the first place, but if you do that, he notices that these two parallel electric current carrying wires either attract or repel one another. That is, they attract one another if the currents are flowing in the same direction, that is, the currents are parallel to one another, and they repel one another if the currents are opposite or anti-parallel to one another. So let's just write that down. He finds that two parallel currents attract one another. So parallel currents attract one another, and two anti-parallel currents repel one another. And this is exactly what we are going to be doing in lab this week. On the previous page, page 87, he mentions some of the important experimental observations. Okay, so what he says is, first of all, that these attractions or repulsions cease as soon as the current stops. So these actions or forces stop as soon as the electric current stops. That's an important experimental observation that he makes. Secondly, this differs from ordinary electrostatic attractions and repulsions. Why does this differ from ordinary electrostatic attraction and repulsion? Well, because in electrostatic attraction and repulsion, if you have two of the same charges, say two positively charged objects, they repel one another. And if you have oppositely charged objects, they attract one another. So notice here with electrical currents, if you have two of the same kind of current, you might say, they're in parallel to one another, those attract one another, whereas opposite currents, that is oppositely directed currents, anti-parallel currents, they repel one another. So this seems to be a different sort of thing than Coulomb attraction and repulsion due to charges. Third, he mentions that when the attraction is strong enough so that these wires touch one another, they stick together. When the current carrying wires touch one another, they stick or they stay together. Notice that this also is different than when you have two attracting charged objects. So if you have a positively charged ball and a negatively charged ball, they attract one another, but as soon as they touch one another, the charges, they come to electrostatic equilibrium. They go to the same voltage, the same electric potential, and then they no longer attract one another because they come to equilibrium. So again, he's highlighting this is different than what people are accustomed to with electrostatic phenomena. And finally, he mentions that this attraction and repulsion occurs in vacuum or air. So it doesn't seem like, it seems like you can't block this effect. If you have vacuum separating them or air separating them, and he doesn't mention this, but if you put other objects between them, so you try to shield this, you cannot easily shield this effect. Now let me say a few other things about the apparatus. If we jump back to this page, let me mention some of the details of this experimental apparatus. How does he get the electrical current into this apparatus? Well, you probably see on the left side of the diagram, there's a letter labeled R and another letter labeled S over here. And those two objects are cups filled with perhaps liquid mercury. And notice that there's a wire coming out of each one of them. One of them goes over to a post where the horizontal wire AB stretches across, and then that is attached to another wire that dips into cup N on the other side. And then you have cup S on the left with a wire dipped into the liquid mercury, and that is attached to the post P, where the current, if you bring a current in from cup S, it goes up through P over to X, and then what happens is you have this suspended wire that goes down to CD up to Y, down through Q, through a wire over to cup U, and then the current can go out there. This this square-looking wire XCDY is balancing on top of a couple of joints that allows it to swing back and forth. There's an insulating rod between E and F, so the current cannot go directly from X to Y through EF. Instead, it has to go down through X, C, D, and up to Y. Now, this whole thing can swing back and forth, this square loop, because why is that important? Well, if a current is going from C to D, and also a current is going from A to B, you want to be able to observe the force between them. That force is determined by whether that swinging section CD is able to be attracted toward AB or repelled from AB. So that's the idea of the apparatus. And by the way, those cups R, S, T, and U that are filled with mercury, one can take a battery and take the wires coming from the battery and dip them into the cup at R and T, for example, and that can drive this current through the liquid mercury conducting metal that allows the current to go from cup R over to cup T. Okay, tell you what, why don't we stop there, and then I'll have one more lecture where I describe the conclusion of Ampere's writing and talk about how he describes permanent magnets as being stacks of electrical current.